Okay, thank you, Shi, for the introduction, and thanks the organizer for putting everything together. Wonderful opportunity for everyone to virtually meet each other during this tough time. So this is journal with Chengdu, and I think maybe my slides is something okay, and okay, good. And Yanzhi Zhang and Qinglin Tang of Sichuan University, and some current PhD student Teng Zhang are doing this one. A brief outline. I will brief motivate you what is the quantized, what is in superconductivity, superfluidity. So mathematical models. There, when first introduced a central vortex state, like a soliton in extension of soliton in 2D, some of that. And there's a call size. If call size go to 0, so there's many vortices. Then there's a reduced dynamic law, kind of set of ODE system, which is governing the vortex center dynamics. So kind of like what you for like a particle model for the vortex center. Well, based on the reduced dynamic law for getting the Landau equation, we can talk a few things there. Of course, I will talk about this kind of things for Schrdinger equation with nonlinear wave equation as well as unbounded domain, something like that. We know a quantized vortex is kind of called particle or topological defect. So they are in a complex order parameter or complex scalar field, so psi. So at the vortex center, the order parameter has to be 0. So in your fluid language, at the vortex center is a vacuum. And near the vortex center, so with x0 vortex center, near the vortex center, psi can be locally written as square root of rho exponential I phi. So rho is a density, phi is a phase. So if any gamma is a closed curve around x0, the phase, the integral along gamma, the phase has a 2 pi n. Well, n is called as the circulation index or 1D number. So this kind of quantum vortices is kind of a key signature to support superfluidity. So they support the dissipationless flow. So this kind of flow, when they flow, there's no friction. So this is kind of a cartoon to show like a quantum vortices in liquid helium 3. Their temperature is like a micro Kelvin, something like that. So this is cartoon. Of course, here this is real experimental result. Like a quantum vortices in type 2 superconductor. So each white dot is a quantum vortices. So here also an experimental result for like in quantum vortices in both condensation. You can see this, the top one is many particles in the harmonic trap. There here there's no rotation, so ground state like a bump, a Gaussian type. Well, if this system is a rotation frame, you can see there are little holes. Each hole is a quantized vortices. So basically, the quantum vortices exist in superconductor modeled by Guillaume equation, liquid helium 3, decoded by two fluid model coupled Euler system equation. Like you have Vn and rho n, the velocity and density for normal component, and rho s, Vs for superfluid component. So they couple together. So they also can use if you use the Gross-Plissé equation to model as a phenomenological model to model this one. Also, the both condensation is a kind of nonlinear Schrdinger equation or Gross-Plissé equation to model. You also in nonlinear optics or propagation of laser beam, there you use nonlinear Schrdinger equation or nonlinear wave equation, even nonlinear Kinetic equation to model this kind of problem. So here is some kind of typical mathematical model. Here psi is the order parameter, complex order parameter or wave function. Like you get the Landau equation for superconductivity or nonlinear heat flow, complex flow. Here psi, t is time, psi is wave function, the order parameter. I intentionally write all the equation right hand is the same. Right hand is Laplacian psi plus 1 over epsilon square, 1 minus epsilon psi square psi. Could be on whole space in 2 dimensions or a bounded domain omega with different boundary condition. So this is Landau equation or complex Landau equation or nonlinear Schrdinger equation or nonlinear wave type equation. Nonlinear wave type equation or even nonlinear Kinetic equation. So here psi is a complex valued wave function or other parameter. I have a parameter epsilon is a diminished parameter, which is sort of the cause size of the problem. You can see in that problem, the nonlinear part is k, epsilon small. So basically, in space, the typical scale is order epsilon, and in time, it's like for Landau equation or Schrdinger equation, the typical wavelength is order epsilon square. Of course, in wave type equation, the typical wavelength is order epsilon. Okay, if you introduce so free energy or the functional, you can say since there's 4 equations, the right hand side is same. So if you introduce the free energy or the functional, you can say the Schrdinger equation representing the dispersive system, so that the energy or the density, of course, the modified density, they are all conserved. So this kind of dispersive system, they admit, so because the solutions, so the particle-like solutions, like in 1D, like soliton solutions, in 2D, kinks or vortices, what I show you here. If you get the Landau equation is a dissipative system, they're energy diminished system. So the single or central vortex states we call bright tail. So if consider for simplicity, consider omega is whole space in R2, you can see take an ansatz psi equal psi of x equal phi n of x equal fn of r times exponential I n theta. Here r is the polar coordinates, n is the one-dim number. So I plug this ansatz into a system, I end up with this fn for this kind of 2-point boundary value problem, and at f r equals 0 is 0, r equal 1. So this is so top here is the fnr for different n. You can see when r equals 0 is 0, when r equals infinite is 1. And formally, one can, so the middle part is like the absolute value of phi n. You can see the inside the origin is 0 of the density and 1 outside. So for fnr asymptotically, you can see when r between 0 and order epsilon, which is fnr is a constant times r over epsilon to power epsilon value n. Well, if r much bigger than epsilon, is 1 minus n square over times epsilon square over 2r square. Basically, near the core, the fn is like a grow in terms of r polynomially, and at far field, the leading order is 1. Next order, the fnr decay quadratically in terms of 1 over r square. So this is the phase. You can see when n equal 1, it's on a when you go 1 round, the 2 pi jump. This next one is n equal 5. If you go 1, let phi theta go to 1 round, there are 5 times 2 pi jump. So of course, if you're interested, all this kind of particle-like solution, are they dynamically stable? Of course, you know, if you set out the parameter, rho is density, v grad s is called quantum velocity, and g is current. So of course, one can study. There are some analysis for Landau type, but for Schrdinger type, always some kind of assumption. So of course, one can study numerically. Due to time, I don't want to show you this movie. I just give you the result. So basically, if I just have one, this vortex state, I do some perturbation. For Landau type, I can do perturb at the initial data. If you do little perturbation, when n equal plus minus 1, they're dynamically stable. That means if you initially have a one number n equal 1 or minus 1, after some perturbation initial data, dynamic long time later, they still want number 1. Well, if n bigger than 1, you know, the dynamic unstable. Basically, the patterns split to n vortices when t much bigger than 1. This is for this dissipative or Schrdinger wave type equation. However, for linear Schrdinger equation or GPE, so this time if you perturb an initial data, they are dynamically stable for any n because the angular moment excitation is conserved. But however, if you perturb the internal potential, for example, then n equal 1 or minus 1, the dynamical stable if n bigger than 1, and epsilon n bigger than 1, dynamical unstable, something like that. Okay, of course, since n equal plus minus 1 is dynamic unstable, you are interested to study what is interaction. That means initially I take my psi 0 of x equal a product of j from 1 to n phi of mj x minus xj0. So xj0 basically is the location of the j's vertices, and mj equal plus minus 1, and phi m of x is the stationary vortex state. And also I can multiply a phase impending and initial data. So basically initially I have capital N vortices, and suppose they are well separated. Let me say basically xj0 and xm0, the distance is much bigger than epsilon. And also I suppose, okay, this one. And then you just suppose, okay, suppose then you plug this, suppose solution psi of xt could be something like a product of psi j equal 1 to n phi mj x minus xjt, where xjt is the vertex center of the j's vertices at time t. So you plug plus higher order term. So you plug this ansatz into the energy. You do some analysis. You will find, as long as the distance, initial distance, they are much bigger than epsilon, or the distance goes to infinite. In other words, so-called the distance is much bigger than epsilon. The left epsilon goes to 0, or the initial distance is fixed. That epsilon goes to 0. The xjt will will follow ODE, and then later can prove rigorously this reduced dynamic law. So you can see this here give you. Let my capital X is x1, x2 to xn, which is the set of points in R to n, which xj of t is what is center at time t. So then I have introduced a functional w of x, which is like this one here. So remember this here, my mj mk could be 1, could be minus 1. So for Gibbs-Landau equation, I can dissipate PDE, my so-called my capital xj will follow this second order, this second order ODE system, nonlinear. So basically, vj is x dot. Oh, sorry. Follow this first order ODE. So vj is xj dot. So the velocity of j's particle will follow this one. Okay. And for Schrdinger equation, well, this is from John New of many people conferences, include Wei Nan and Fang Hualin and his group, and also Bochum from from French group. And for Schrdinger type equation, you have a j is a rotation matrix 0 minus 1 1 0 j times xj dot vjt. Of course, vj equal xj dot. Follow this one, the same. And for then the wave equation, which is a second order ODE, like a xj double dot, this one. So you can say here, you can say again here, this right hand side also almost the same, but the left hand side here is vj here, but the rotation matrix j, capital J. And for Schrodinger wave equation, this xj second order ODE system. This one similar as many people of you studied this dynamics for this correct dynamics for something. But remember here, my mj and could only can be taken integer plus 1 and minus 1. Of course, how to study from PDE to ODE system, for Gibbs-Landau equation, they show for African ODE, you can study the qualitatively behavior. For example, if I only have a pair of vortices, then the capital N equal 2 and the M1 equal M2 equal 1. The vortices will undergo the repulsive interaction. If the vortex dipole, the N equal 2, the 1 is plus, then 1 minus. They undergo attractive interaction. And for example, the pinning effect, the other. So from this ODE system tell us. So we recently studied this ODE system more intensively. What we can see more from all this ODE system. Then for Schrodinger equation, this vortices become like a point vortices, like in ideal field, and of course the PD like high order radiation, something like that. Of course, for this ODE system, for this ODE system from Gibbs-Landau type equation, of course, for example, if you have a plus minus, the final time the two vortex center will go together. That's like a blow up or some kind of merging of that one. Well, for Schrödinger equation, you can see at least for n equal 2, 3, or 4, one can show that no matter you initially have all the same sign, or you have a different one-in number, like some plus one, what is it, some minus what is this? You can always show this ODE system is global, well posed. So from our numerical simulation system, so this ODE system is not the initial what is location, they are distinct. The system, they are never two go together. Okay, so now we try to, from this ODE system, what we can see more. So first we consider the ODE system from the reduced dynamic law from Kinetic equation. So this is the ODE system. So of course here xj dot equals this one. Again, I want to remember that the MGML could be 1, could be minus 1. So I define so mass center. So this x bar t is the average of all the location. Then you can show that the x bar t is a conserved quantity, and also the energy, the W, the W of the xt, this is decreasing. Of course, there's some like that properties. For example, if you for all initial data, you shift 1 point, the solution shift 1 point, and also do a scaling. You can do also scaling for the solution. Also do rotation for the initial data with one, like a Q is a rotation matrices. The solution also rotation, this one. And also, for example, if I have n vertices, if initially they are spanned uniformly on a circle with radius a, you can solve this ODE system analytically. For example, if n equal 2, n equals 3, n equal 4, for n and n, basically they are moving outwards along the line, connected initial location and the origin. And if n equals 3, and if I have one, what is it at the origin, the rest n minus 1, they're uniformly along the circle. Again, the center one doesn't move, and the rest n minus 1, they move outwards. This is easy to understand. Just plug use the symmetry. If initially have 2, what opposite what is dipole? Then you can use to show that here plus minus initially this is from ODE. Of PDE, the quality is the same. And of course, you can solve any solution analytically. You can see the solution when basically at t equal a squared over 2, the two vertices will merge at the origin. The next case is if I have n vertices, n bigger than greater than 3, but the opposite. I have one origin, I have minus 1 in vertices, and the rest n minus 1 with a plus 1 vertices. Then you can solve again. You solve origin one stays there, but the rest will move into here. You can see my n equal 4 is a so-called is a critical number, because if n equals 3, they still merge. The 2 plus go to the move to the center, merge with the n minus the n equal minus 1, and after merge, there's only 1 plus left over. But n equals 3, which n equal 4, which is the initial data is a equilibrium, but this is unstable. But n equal 5 and the upper and more, then they move outwards. Because n equal 4 they don't merge. There's this equilibrium, and less than 4 they merge, and greater equal 5 never merge. Then also we can start using the non-autonomous first integral. So of course here we suppose initial data we have capital N vertices. So from ODE system, I suppose among them I suppose I have n plus number of plus 1 in vertices, and n minus negative minus 1 vertices. Of course the sum together equal n, and I define m0 equal this one. Then I define this h1 xt, h2 xt, and h3 xt is this one. They need to show that if xt, xjt follows ODE, then h1, h2, and h3, they are 3 non-autonomous first integral of this ODE system. So with this one, we can show that if I have n vertices, they have same one-day number, then there are no phantom collision. Then the global existence of the ODE system. And in addition, so at least the 2 vertices will move to infinite when t go to infinite. In fact, we can prove a stronger result that for any bounded domain, when t much bigger than 1, there are at the most 1 vertices in this bounded domain when t very large. And also we can show that the so-called if I define the distance between any two vertices, DGL equal xj minus xl, the absolute value. then if n greater than or equal to less than or equal 4, and the n vertex have same one number, then one can show that this is the minimum distance and the between any two and these two are monotonally increasing. However, if n bigger than greater than or equal 5, this no longer, there are some cases that are no longer true. So this d minimum is, I think, is the minimum distance between the any two vertices, and the capital D minimum is the distance square. And we also have some cases. If n equals 3, we can see more long term behavior. If n equals 3 and the same one number, if initially the 3 vertices are located along a line, then when t equals to infinite, we can see that 2 vertices will go to infinite. The one in between will move to the center of the initial of the 3 vertices at the initial location. And if they are initially not a collinear case, then the 3 vertices are on any triangle, then at t large enough, then so-called the 3 vertices will approach to a right triangle when t large. So initially, this 3 vertex is located at any triangle. Then when t large, the 3 vertex will approach to of course a right triangle. Of course, the radius of the distance to the origin is go to infinite, something like that. And then one can have this kind of configuration that, so for n equals 3, we have like a similar as like orbital stability of self-similar solution. For example, initially we can define some so-called so this is something like x2 t is so-called with you can say the distance, the radius, the distance to origin is like grow like at t to power 1/2. The x2 0 is some initial is like a right triangle. Then for any initial data, so this one will so-called the distance of xt minus some center value. They will go to they will approach to this solution up to rotation, something like that. So we have this kind of results. So similar of this for so-called for everybody with the same one number for any n, we have some result. For n equals 3, you have some long-term behavior. Of course, if the opposite one number, then initially have some plus, some minus. That we can show that suppose the n vertices, so that means n plus minus n minus less than n. So we remember we define m0, which is m0 is here. So m0 equal n plus minus n0 square minus n to power divided by 2. So if m0 less than 0, you always the phantom collision. You can always show that when t approaches t max, then so at least 2 vertices they go to the same location. So if m0 equals 0, the solution of solution is bounded. Then all solution will go to the bounded. So of course m0 equals 0, they are very special setup. And if m0 bigger than 0, there is no phantom collision. Then the global existence of the solution. Then we have also some other. This I can skip here for simplicity. Again, also we also give some necessary condition for collision. That means if for n vertices and if they form a collision cluster, then there have to be m0 less than 0 and h10 equal nh20 and h30 equal n minus 2 h20. So that's the 3 because the autonomous, non-autonomous. So first integral must follow this relation. And we also give us a necessary condition for an equilibrium. That means if form a equilibrium, then my n plus must be equal 1 over n plus minus square root of n. This one less than n, something like that. So of course, if n equal 4, so if n equal 4, n plus equals 3, n minus equal 1. This service condition. Then we also have some collision pattern if n equals 3. So here I have suppose I have M1 equal M3 equal 1 and M2 equal minus 1. Then we show that if initially I have 3 vertices, if the initially they are so-called on a say a right triangle, sorry, a triangle with two segments with same length, then so they will so the 3 vertices will merge, will collide at the so-called at the x0 at the center of the triangle, something like that, and the collision time is equal h10 over 12. Of course, if initially they are so-called the triangle, one is long, one edge larger, the other is smaller, then the one with short distance, they will merge to each other, and something like that. So that's why. And then we also have some for Schrdinger type equation. So this is the ODE system. So remember here I have a G equals the rotation matrix here. Then we define assigned mass center x tilde t equal 1 over n mg times xg t. So this one. Remember, of course, if mg the same one number, so this one is the assigned mass center is same as the previous one. But of course, if mg has a plus minus sign, these are different. And for Schrdinger type equation, this assigned mass center is conserved. And also the energy is also the capital W tilde equals this one, because this one is also conserved from this ODE system. And again, we can show that if initial have n vertices, they are uniform around circle, and they will rotate each other because the rotate on circle, but they are counterclockwise with the frequency n minus 1 over a square. Again, if I have capital N greater equals 3, initially 1 at the origin, the other n minus 1 uniform on a circle. Again, the original one center will stay there due to symmetry. The rest n minus 1 will rotate counterclockwise with n minus 2 over a square. This one frequency. And if initially have 2 vertices, you can easily solve their move parallel. So this is a solution, and you can solve. You can easily show this solution set as the ODE system. And again, initially have n greater equals 3. What is opposite vertices? 1 at the origin, which is minus 1 the number, and the rest n minus 1 at the uniform on a circle with plus 1 the number. So you just again, original one is stays there due to symmetry. However, because now again n equal 4 is critical. N equal 4 is a still equilibrium, and n equals 3 they rotate clockwise, and n greater equal 5 they rotate counterclockwise. Again, n equal 4 is some kind of critical number. So here, of course, so here, interesting. Of course, for this Schrdinger type of equation, you can use if n very large. To our understanding, there are no collision, but cannot prove it. We can n equal 4, we can do it. But bigger than 4, of course, the assumption is for this ODE system, if initially you have n vertices, they are distinct. Then any 2 they are not the same. So seems they stay over each other globally. No, whether of course if they are same one number, you can just prove. But if they are opposite one number, seems we cannot do it at the moment. And also interesting, for example, here, if you initially they are like if you have 4, 2 are close, the other 2 they are close. But this 2 separate 2 cluster, then short time the 2 cluster will move like a leading order. They are move like a similarly. So here symmetry is interesting. If you have n equal 2, if 2 one number is the same as what is pair, they rotate each other. If what is dipole, they move parallel to infinite. Of course, if you so this is from ODE tell us. From PDE, then of course for Schrdinger type equation, you can solve PDE. Then basically the qualitatively the dynamics from PDE is similar as ODE. However, for Schrdinger type equation, when the cos size, the distance, if the distance is less than some constant times cos size. So if you have one number, the 2 one number, they are opposite. What is dipole? In fact, they merge to each other. They're not. So ODE tell us they go parallel, but the PDE they tell they merge. If the cos distance between two vertices is smaller or at the order of core size, the ODE basically gives the run dynamics qualitatively. Then people also study unbounded domain. But unbounded domain, Schrodinger equation is scaling the same, but if for Guillaume equation, you need to multiply this scale. Look at the longer term, you need to multiply the PDE at a lambda epsilon, lambda equal 1 over log epsilon, something like that, so that you see dynamics. So here, so of course, given in this data, of course, you have a different bound condition like a Dipole Neumann, or here there are 3 scaling. One is the size of the domain of omega. The other is the smallest distance between two vertices, and the third one is the one in the core size of each vertices. So of course, when for fixed n number of vertices, if x equals 0, there are a lot of results. Of course, if you fix like a left x equals 0 and also n go to infinite, you know, the Safety have wonderful results 5 years ago on this for Schrodinger for this study. So of course for fixed n, there are lots of results. Let x equals 0, so the house was a limit. Of course, if you let the x go to 0 and n go to infinite, they are very challenging PD study. So of course for bounded domain, the ODE system, like of course you can say you need the whole space ODE system plus, okay, here I have a R. So due to boundary effect, the R is something like a solve like a Laplace X. The capital X is the location of the vertices, and little x is the domain. So basically, like for Guillaume equation with the digital quantum condition, this is the ODE system. Basically, it's kind of the ODE with a non-local R, which depends on the location of the vertex location. For Guillaume with gross potential equation, so this is some ODE. So basically, the capital R follow different bound conditions, something like that. I don't want to bother you here. And for Guillaume equation for the noise bound condition, this is the ODE. This is the dynamic law. For GPE equation, this is the dynamic law. I think my time is almost gone. Maybe I don't know, but I just show some result. So you can say this is a vertex pair for with digital bound condition. The left one is for the gross potential dynamics. So the right hand one is for Guillaume. So this is dispersive dynamics. The right hand side is for dissipative. You can see how they go. You can see for the gross potential equation, they rotate with each other. For Schrodinger, for Guillaume equation, they move repulsively. This is for vertex pair. So here is for what is dipole. So then what is our antivertices? So one is when number 1 minus 1. Again, the left hand side is for Schrodinger type or Guillaume type. So for gross potential type equation, right hand side for Guillaume type equation. You can see how to say. You can see for gross potential equation, initially they move parallel, then move to boundary, then merge. For Guillaume equation, they merge very quickly to each other. And okay, I don't know, this I skip. And I also show some like here I show some what is the pair for gross potential equation with digital bound condition, but with digital bound condition. So you can see this is for no initial impinging. Here I have impinging like h equal x plus y. So this impinging will affect the dynamics. And I can skip this one. Okay. So and also maybe okay, let's skip this one. I just show you. So for what is for 3? If for Schrodinger type equation, if I have 3, what is it? Initially, you can say this one is what is with 3 1 in number, and this one with 2 plus 1 minus in center. You can see how do they move. For bounded domain, you can say so for the left hand one, the same one in number, they rotate clockwise, and after some time, due to boundary effect, they move very interesting dynamics. And the left hand side, due to they rotate clockwise, counterclockwise, but after some they merge. So left hand they never merge. I think I'll finish this one with the last. So this one is also show the Schrodinger type dynamics, GP dynamics, Schrodinger type dynamics, dispersive dynamics, and on rectangle domain with periodic bound condition. You can say initially I have 3 vortex dipole. So plus minus plus minus plus minus. The bottom one is the density. So the blue is 0. The top one is the phase. You can see each has one number. So I have 3 pair. So I have 3 dipole. You can see when time evolve, they show some kind of leapfrog effects. So you can see the one with the large distance moves smaller. You can see they just like a leapfrog. The different pair they move like a leapfrog. I show you maybe again. You can see they just show like a leapfrog. Like this is also observed in 3 dimensions for what is run in the dispersive dynamics of what is run. They show this observed experimentally. Here in this kind of thing, we can show numerically here for unit 2D. Okay, I think I finished here, and due to my time is finished, I think I stop here.
Do you have any simulation for n quite large to see?
Yes, we do like n equal 50, something like that. But depends on epsilon. If your epsilon smaller, your n cannot be too large.
Okay, sure. Yeah.
But you have 2 scale. One is epsilon, the other is n. The other the domain size. Basically,
so it's very large. How different is compared to, let's say, simulation of fluid dynamics? Any interesting difference?
My mesh size should be at the order of the epsilon, the core size. So basically, my first points should be the so-called the size of the domain over epsilon to power dimension. F2D, basically, I need the dimension size over epsilon to square. This number of points is the minimum. And my time step should be taken as like this epsilon square or something like that.
Yeah.